by 3, which is true. Okay. Step 2, we want to show that pk implies pk plus 1 for any integer k greater than or equal to 1. Okay. So now k greater than or equal to 1. So we assume that pk is true. We assume that pk is true. So that means we assume 2 to the power of 2k minus 1 is divisible by 3. For any integer k greater than or equal to 1. And we want to show that pk plus 1 is true. That is to show that 2 to the power of 2 times k plus 1 minus 1 is divisible by 3. For any integer k greater than or equal to 1. Okay. So now we're going to start to prove. Okay, we're going to start to prove. But before we do that, this information is divisible by 3. What does it mean? It means that you have 2 to the power of 2k minus 1 equals to 3 times a. Is that right? Okay. And you want to show that this is divisible by 3. So it means that you want to show 2 to the power of 2k plus 1 minus 1 equals to 3b. Is that right? Divisible by 3 means equals to 3 times something, right? Okay. So I'm going to put a note here. Note that we assume 2 to the power of 2k minus 1 equals to 3a is true. For any integer a. And we want to show 2 to the power of 2k plus 1 minus 1 equals to 3b is true for any integer b. Okay, this is just to remind us what we would like to have at the end. Because we want to have divisible by 3, so that means it must be 3 times something. Okay, now you can start working on this, but we're going to consider 2 to the power of 2 times k plus 1 minus 1. Okay, and at the end we want this one to be equal to 3 times something. So this is equal to 2 to the power of 2k times 2 2 to the power of 2, and then minus 1. Is that right? You start with this first. Why do you start with this? Because this is what you want to show. Okay, so that's why I start with the left-hand side. And what should we have on the right? 3b. Okay, 3b. And b can be any integer. Okay, so now we want 3b on the right-hand side. So you do whatever it takes until you get 3b. Okay, but keep in mind b can be any integer. So we start with that one on the left. So from the left-hand side, what we have is 2 to the power of 2k times 2 to the power of 2. Just this part. Do you agree? Okay. And next, we're going to work on that. Why don't you try to work on this until you get 3 times something and see if we may not have exactly same step, but if we have completely different, then it's a good time for you to ask me, this is the way I think, is it okay? Something like that. Because for induction, it's something that not like if you have 1, you need to go to 2, and then you need to go to 3, not like that. Some people will start from 1 and then go to 5, and then 3, and then 4, and then 2, and then go to the end, like that. So it depends. Right now, I think this one you should be able to do, so why don't you try? You need to continue until you get 3 times something. Make sense? Okay. it up to this step. Okay, and because 2 to the power of 2 is 4, is that right? Okay, so that's why I have my second line. And 4 is 3 plus 1. Is that right? When you have 3a plus 1a, it will be 4a, right? So that's why I wrote down that will be a 4. And only this part is 3a. Anyone would like me to explain again? Okay. I'm going to go back to line 1. Are you okay up to here? Yes. 2 to the power of 2 is 4. Are you okay up to here? So right now, from 4 here, it's like when you have 4x, that is the same thing as 3x plus x, is that right? Yes? So this one, I have 3 and 1 here. That will be 4. And after that, this one here is the same thing as 3a. How do I get this? By inductive hypothesis. By inductive hypothesis. And after that, you just need to simplify. And you're going to get 3b. And your b is integer. Because a is integer, 2 to the power of 2k is also integer. And remember last time we learned the sum of 2 integers is integer. Okay? So now, that is pk plus 1 is true. Hence, pk implies pk plus 1 for any integer k greater than or equal to 1. Therefore, by induction, Pn is true for all n greater than or equal to 1. Okay, example 5, please. We are not going to do example 6 because I think that would be too much for you for example 6. But if you can do it, that's good. Because the induction, as I say, I cannot tell what you need to prove. I can only tell the step that you need to do. And a different proof, I mean different setup, you're going to need to use a different approach no matter what. Okay. So right now we're going to do number 5. This is what I want you to do. I want you to do it by yourself. Okay. And once you are done, I want you to come and check with me. I want you to make sure, I want to make sure that the way you think is okay or not. Because from my experience, sometimes you kind of randomly select a number and you think that is right, which is not. We cannot randomly select a number and put it into the proof. We need to have explanation. So I'm going to do example 5 because I don't have solution right now. Okay, and then I'm going to show you once I'm halfway done. One thing I think I didn't mention. Do you realize something here? Everyone look, I'm gonna circle in red. We want to prove that it's true for all. Okay, for all n greater than or equal to 0. But when we prove, we let them to be true for any n. Okay, and that is for any k greater than or equal to 0. Because this is the way it works. We want to prove for all, but induction, you can only show that it's true for any. Okay? And if it's true for any, then at the end you conclude that for all will be true. Make sense? Okay. It doesn't mean that when you prove step 1 and step 2 of the induction, you need to prove for all. As long as it's true for any k. And in conclusion, it will be true for all n, like that. So we wrote this one down. I wrote down on purpose. We want to prove for all, but when we do the induction, we use for any. Okay, and you see that at the end, by induction, it's true for all. Make sense? Okay. It doesn't mean that you can put all or any at any time. Okay, because by the theory, it has to be for any k. Are you done? Hi, all? Yes? Okay. Um, this is only thing I want to point out. You see that this one I copied from the first question today. So I only changed my PN. I only step 1, my A start at 3, like that. So 7 is less than 8. So this one is true.
No, yes.
Yes. Okay. And then step 2, we assume PK is true, and then we want to show PK plus 1 is true. If you ask me, Ajahn, do we have to write this whole thing? The key word is just the one that I highlight. However, you're going to need to write down, for example, assume PK is true, and you want to write up to here. When you do the proof, you will stop somewhere. So basically, you're going to need to write this one down, that this is true. Okay? So then when you do the proof, you know that this one is the information you can use. So the bottom line is you almost have to write exactly the same thing. Almost, okay? And then we need to show this one. So this is the bottom line that we want to show. We start with the left-hand side, okay? I think Ajahn Saifon is kind enough that all her example, you need to start with the left-hand side. Because sometimes you may need to start with the right, will be easier, okay? If you start with the right-hand side, will be easier than the left, but anyway, start with the left-hand side will work most of the time, almost like 99% of the time. So we consider 2 times k plus 1 plus 1, this. So from here to here, we have 2k plus 2. Everyone look and try to follow. This is the left-hand side that you want to prove. And you multiply 2 in, you have 2k plus 2, is that right? Okay. And right now I just switch 1 and 2. Are you okay up to here? Yes. And 2k plus 1 is less than 2 to the power of k. Are you good up to here? Okay, I think I forgot to write down the explanation. That because this is by inductive hypothesis. Okay. So next, we have it up to here. And we want 2 to the power of k plus 1. So you know that if this one we have 2 to the power of k again, you will get to 2 to the power of k plus 1. Is that right? So that's why I think from 2, I need to change to 2 to the power of k. This is the way you should think. We want to change from 2 to 2 to the power of k. Can we do that? Yes, we can. Because 2 is less than or equal to 2 to the power of k. Because we know for sure that 2 is less than 8. And 8 is less than or equal to 2 to the power of k. Because k is 3. Is that right? Our k starts at 3. So we know that this one will be greater than or equal to 8. And we know that 8 is greater than 2. So therefore, from 2 here, is less than or equal to 2 to the power of k. Make sense? And this is a must. When I taught the class, I have to tell you this one, Ajahn Saifon will be the one who marked the exam. I asked her already, she's not that picky about wording. However, something that is important is a must, like this one. Because if you don't write down the explanation here, we will not know that you know what or not why we need this. Because sometimes students tend to work backward anyway. Like you know that this is what you want, so you go from here to here and here to here without knowing anything, okay? And it may not be true. So try to explain every step, okay? And from here to here, I think that's quite straightforward. And that will be the conclusion. Like that. So we have 2 examples left, that is example 2 and example 6. Since example 6 is about the sequence, so I'm not going to do example 6, but you can try at home. Let's talk about the exam. I'm not going to say much because Ajahn Saifon's class already finished. She didn't have time to meet her student. So I'm not going to tell anything much because that's not fair for that group. The only thing that I can tell, which I already told you in my calculus class, but if you are not in my calculus class, you will be provided the laws of inference, the rules of inference, this one, and the logical equivalence, like this. Okay, so you will be providing this table, and you will be provided this one. This will be the 2. You don't need to memorize. The question contains, the exam contains 9 questions. Looks like it's a lot, but some of the questions you will finish within like 2 lines or 1 line. Okay, so it won't. You don't need to worry about that. That's a lot or not. Okay, and we have the logic, we have the proof, and we have the induction.